So in previous lecture, that is lecture number 12, so we have seen, yeah, so first we have defined upper sum and lower sum, and then we have seen the geometrical interpretation of upper sum and lower sum. So after that, we have proved one lemma, that is, see, lower sum of f with respect to subdivisions tau is always less than equal to upper sum of f with respect to subdivision sigma. So tau and sigma are any two subdivisions. So these are general subdivisions, and always, so whatever your subdivision, lower sum is always less than equal to upper sum. So that was the statement of that lemma, and we proved that lemma. See, so we proved this lemma. So we used definition of refinement. So we add one single point in the original subdivision and we obtain its refinement. And for refinement, so we obtain a result, that is, so upper sum on refinement is decreases, means if we increase the number of points in subdivision, then corresponding upper sum in decreases and lower sum increases. So if we refine the original subdivision, then upper sum decreases and lower sum increases. So that result first we proved, and then using that result, we proved the required inequality, that is, a lower sum of f with respect to subdivision tau is always less than equal to upper sum of f with respect to subdivision sigma. So that was the proof of this lemma, and already we have seen it in detail. So after that, yeah, so there is one remark, that is, so from the preceding lemma, it follows that so upper sum of f with respect to sigma so is always greater than equal to lower sum of f with respect to sigma. So if we take greatest lower bound of all upper sums, so we are taking greatest lower bound with respect to sigma and least upper bound with respect to sigma. So in that case, so this greatest lower bound of all upper sums of f with respect to sigma always greater than equal to lower sums. So where greatest lower bound and least upper bound are both taken over the subdivision sigma of AB. So sigma is variable, so you can vary all subdivisions of this that closed interval AB on which that function is defined. So if tau is any subdivision of closed interval AB, then the lemma shows that lower sum is the lower bound for the set of all upper sums of upper sum of f with respect to sigma. Hence, so any lower sum. So in particular, if you take a lower sum with respect to tau, then it will be again less than equal to greatest lower bound of upper sums of f with respect to sigma for every subdivision sigma. So you are taking greatest lower bound with respect to subdivision sigma. So, but this says that the greatest lower bound of all upper sums of f with respect to sigma, and you are taking greatest lower bound with respect to sigma, is an upper bound for the set of all lower sums. So lower sums of f with respect to tau. Hence, you can take, that is, least upper bound of lower sum of f with respect to tau, where tau is any subdivision, it varies, and you are taking least upper bound with respect to tau, which is less than equal to greatest lower bound of upper sums of f with respect to sigma, and here again, so you are taking greatest lower bound with respect to sigma, so which is equivalent to 1, so which already we have written. So here subdivisions, we are taking greatest lower bound and least upper bound with respect to same subdivision, and here we are taking least upper bound with respect to subdivision 2 and greatest lower bound with respect to subdivision sigma. So next we will define upper integral. So what is the definition of upper integral? See, so let's suppose upper Riemann integral, actually it is definition of upper Riemann integral. So you can correct modify it. It is upper or Riemann integral. Yeah. So let f be a bounded function on the closed bounded interval AB. So we define upper integral of fx from a to b. So this notation for upper integral. So called the upper integral of f over closed interval ab. So how we define? So upper integral of f over the closed interval ab. So upper means we are writing this upper means horizontal, yeah, small horizontal line on the sign of integral. So we are writing it. So integration from a to b of fx dx, it is nothing but greatest lower bound of all upper sums with respect to sigma. We are taking greatest lower bound with respect to sigma. So here, so greatest lower bound is taken over the all subdivision sigma of AB. And similarly, we define the lower integral. So here we are writing this horizontal line, yeah, line segment, very small. So it is not minus a. So I'm writing this horizontal line segment at the lower part of this integral. So it is integration from a to b of fx dx called the lower integral of f over ab, and how it is defined. Let us see. So it is lower integral of fx from a to b, which is nothing but least upper bound of all lower sums. So least upper bound of all lower sums, and you are taking this least upper bound with respect to sigma. So this is definition of lower integral, and so I'm just making box for this. Yeah. So this is definition of lower integral, and this is definition of upper Riemann integral. So again, I will make it box. Yeah. See. So what is the upper Riemann integral? It is nothing but greatest lower bound of all lower upper sums. That is smallest upper sum. And what is the upper lower integral? It is yeah, it is the biggest lower sum. So in short, you can write, or for convenience, you can write. Yeah, that is, see, upper Riemann integral is nothing but, so I'm not writing it exactly, but so approximately. So this statement is not, uh, yeah, correct 100%, but approximately you can conclude like this. So upper Riemann integral is nothing but smallest upper sum, and lower Riemann integral is nothing but largest lower sum. So in short, you can conclude in this way. So that is just observation. I'm writing our observation here. It is not exactly correct, but it is just observation. So note here, for simplicity, we sometimes denote upper and lower integrals of f by this notation. That is, we will just write integration from a to b of f, and this note, yeah, this horizontal line on the upper part of this integration sign, and horizontal line at the lower part of this integration sign, integration from a to b. So it stands for lower integral, and this stands for upper integral. So I will not write likewise, that is integration from a to b of fx dx. So instead of this, we'll write just integration from a to b of f. So for equivalently, so one we have, so obviously, see, so lower integral is nothing but the largest lower sum, and it is again lower sum. So upper Riemann integral, it is nothing but, yeah, lowest or smallest upper sum, it is again upper sum, and again upper sum is greater than equal to lower sum. So this relation is obviously there to show that. So obviously, to show that upper Riemann integral and lower integral are equal, so we need to show because lower integral is always less than equal to upper integral. So if we have to prove, yeah, upper integral and lower integral are equal, then we must prove just this inequality, that is, so lower integral is greater than equal to upper integral. So it is sufficient to prove this equality. So it is sufficient to prove this inequality, that is lower integral greater than equal to upper integral. So next, this is definition of Riemann integrable function. So if f is a bounded function on the bounded interval, closed bounded interval AB, so we say that f is a Riemann integrable function on closed interval AB if, so lower Riemann integral and Riemann integral both are equal. So if there is equality, so for this upper Riemann integral and lower Riemann integral, so then in that case we will say that function f is a Riemann integrable function on the that closed bounded interval AB. So this is definition of Riemann integrable function. So note one. So in this case we define, see, so this is the total Riemann integration, and this is a lower Riemann integration, this is upper Riemann integration. So both these values will be equal to this, and that equal value is called the Riemann integration of f from a to b. So we denote, so RAB. So this is set of, what is meaning of this notation? That is RAB. So R stands for, that is set of real numbers, set of all real numbers, and this closed bounded interval AB stands for, yeah, functions defined on closed interval AB. So what is RAB? This set of, it is a class of all functions f which are Riemann integrable on closed interval AB. It is set of all Riemann integrable functions on closed on interval AB. So closed interval AB stands for functions on closed interval AB. So it is set of all Riemann integral functions. Sorry, this is not correct. What I am writing here. So what is R? So R stands for Riemann integrable functions, and this closed bounded interval AB stands for this. So functions are defined on this closed bounded interval AB. So this meaning of this notation. What is the meaning of this notation? The class of all functions which are Riemann integrable on closed bounded interval AB. So next, yeah. So there is one theorem. So let f be a bounded function on the closed bounded interval AB. Then f belongs to RAB, means f is Riemann integrable on closed bounded interval AB if and only if for each which belongs to greater than 0 there exists a subdivision sigma of closed bounded interval AB such that, so upper sum of f with respect to sigma is strictly less than lower sum of f with respect to sigma plus epsilon. So f is Riemann integrable if and only if, so it satisfies this inequality, that is, so for each epsilon strictly greater than 0, so for given epsilon strictly greater than 0, there should exist a subdivision sigma. So for that subdivision sigma, or by taking that subdivision sigma, upper sum of f with respect to sigma strictly less than lower sum of f with respect to sigma plus epsilon. So this inequality is true. If f is Riemann integrable, then this inequality is true for given epsilon is greater than 0 and corresponding subdivision sigma. And if, so for given epsilon is greater than 0, if there always exists subdivision sigma which satisfy this inequality, so in that case, naturally that function will be Riemann integrable function. So this statement of this theorem, so which is the important theorem which gives us alternate definition of Riemann integrable functions. So next, so I will give some homework here on this topic, that is Riemann integrable functions. So definition of Riemann integrable functions. So first problem, so you can solve, yeah, just a minute, yeah. So let's suppose f is a mapping, so fx equal to x for all x belongs to closed interval 0 1. So let sigma be subdivision, and which contains suppose 4 points, that is 0 1 by 3 2 by 3 and 1. of closed interval 0. So you have to just compute upper sum and lower sum of f with respect to sigma. So just find out the value of upper sum and lower sum with respect to subdivision sigma. So sigma is this. Yeah. So this is first problem. Second problem, for each m belongs to m, so you have to take same function, that is fx equal to x, and same interval, that is closed interval 0 1. Just you have to change subdivision, and here subdivision is sigma m. How it is defined? So it is given. It is 0 1 upon n, 2 upon n, up to n upon n. So it is subdivision of closed interval 0 1. So again you have to compute here upper sum and lower sum of f with respect to sigma, and then limit of upper sum and lower sum as n tends to infinity. So just find out this. And last, so let fx equal to x square for all x belongs to closed interval 0 1, and sigma n is again same partition subdivision which is defined in example 2, that is 0 1 upon n, 2 upon n, up to n upon n. And again you have to compute upper sum, limit of upper sum, and limit of lower sum as n tends to infinity. So before that you have to find upper sum and lower sum with respect to sigma n, and then you can take its limit. So do these three examples as a homework. So in next lecture I will continue, that is 4.3, existence of Riemann integrable function. So still then I will stop.